Let's take a look at an example to better appreciate sort of the capability that this frequency and magnitude scaling can give us. So in this case, a circuit has already been designed, so a fourth order Butterworth low pass filter, and so we see the circuit there in the middle of the screen, and so we're told that the circuit was designed with a cutoff frequency of 1 radian per second. And so that's kind of an odd value, but we notice that a lot of these values in the circuit, 1 ohm, 1.848 Henry, 0.765 farad, are sort of easier values to work with than the microfarads, the millihenries, the k ohms that we would normally work with. So what we want to do to this circuit, though, is after this design has been done, we want to now scale the circuit such that it has a cutoff frequency FC of 50 kHz, and we want to use 10 k ohm resistors. So we're going to be doing frequency and magnitude scaling. So the fact that we want to change our cutoff frequency indicates we want to do frequency scaling, and the fact that we want to be using 10K resistors instead of 1 ohm resistors indicates that we're changing impedances, so we're going to be doing magnitude scaling as well. So we can start in either place with our frequency or magnitude. If we go back and we review our equations for sort of our combined frequency and magnitude scaling, we see that our resistor is only affected by magnitude scaling, our frequency is only affected by frequency scaling. So let's start by looking at our resistor, and so our resistor, R primed, we know is just equal to Km times R, so it's only affected by the magnitude scaling. So what we can say from that is we can say, well, our Km is just equal to R prime over R. So, sorry, not R1, this is our R prime. So our R primed is the 10K that we want to use, and our original R value is the 1. So, of course, that's just going to be the 10K or 10 to the 4th. So this is the value for our Km. So let's circle that there. So similar thing for our frequency. So we know our cutoff frequency is going to be changing. So omega C1 is going to equal to the frequency scaling times our original cutoff frequency. And so again, looking at those equations for magnitude and frequency scaling, we see that it's only affected by frequency scaling, not magnitude scaling. So we can rearrange this and solve for our Kf. So that's going to be equal to omega C prime divided by omega C. But remember, we weren't given an omega C primed, we were given an FC primed, or an FC. And so what this is we can say this is 2 pi times our FC primed, what's going to be our updated frequency after the scaling, divided by our original. So plugging in values, we have 2 pi times 50,000, so 50 kHz, divided by our original frequency of 1 radian per second. So if we plug that in, we get that our Kf, our frequency scaling factor, is pi times 10 to the 5th. So I've kept the pi in there just so we don't have to deal with the decimal place for the time being. So now that we know values of Km and Kf, we can use that to figure out values for our capacitor and our inductors. So of course our updated resistor values, we're going to have their 10K by design, but what we want to do is figure out the values for these inductors and capacitors. So let me come back up here and label these so we can keep them straight. Let's call this C1 and C2, and let's call this L1 and L2. So again, going back to those equations for using our combined frequency and magnitude scaling, we can now say our C1 primed is equal to C1 divided by Km times Kf. Plugging in values, we have that our C1 is 0.765 farads, and our Km we found to be 10 to the 4th. Our Kf was pi times 10 to the 5th. So we get that. Plugging in these numbers, we get approximately 2.435 times 10 to the minus 10th farads. And so I've sort of left off some significant figures there, so let me put those in there so this next part will make sense. So putting that into picofarads, we move the decimal place to the right 2 places. We see that C1 is 243 0.5 picofarads. Okay, so now let's do the same thing for C2. So we're going to use that exact same equation. So C2 primed is equal to C2 divided by Km times Kf. Plugging in the value of C2, we have 1.848 farads divided by 10 to the 4th from our Km, 10 to the 5th times pi for our Kf. And so if we plug that in and change that to picofarads as well, we get that's approximately 588.2 picofarads. And so again, pico is 10 to the minus 12. So these are relatively small capacitances, but definitely a much more realistic value than a 1.8 farad capacitor. So now we want to figure out the value of our two inductances. So our L1 we can find by doing Km divided by Kf times our original inductance, L1. So that's going to be 10 to the 4th divided by 10 to the 5th times pi times our original inductance for L1, which was 1.848 henries. And so that is going to be approximately 58.824 millihenries. So milli, of course, 10 to the minus 3. So that's our L1 value. We find our L2 value in the same way. L2 is equal to Km divided by Kf times L2. And we have 10 to the 4th divided by 10 to the 5th times pi times our 0.765. Plugging all of that in, we get that this is approximately 24.351 millihenries. And so what we see is for these capacitor and inductor values, these are more realistic values. And in doing this, we didn't have to redesign the circuit. We could use a circuit that was already designed. We knew the cutoff frequency, and we were able to scale impedances to get more realistic values as we see here, as opposed to those very large inductances and capacitances. And we were also able to shift our frequency to a more realistic corner frequency. So instead of having a cutoff at a extremely low 1 radian per second, we were able to move it up to 50 kilohertz. So this shows sort of the power of being able to use these scaling properties.